Okay, so today we are going to continue our discussion of second order linear homogeneous differential equations. So does anybody remember what those were from last week?
Second order, so it has a double prime.
Second order, so it has a double prime. I love it. Y double prime. I actually did forget one word. We had constant coefficients in there, right? So we had y double prime plus ay prime plus by equals 0. So that 0, that's the portion that makes it homogeneous. And then it's linear because none of our y's have any type of like squared or anything. They're just, all the y's are linear. So how were you solving these? What were you doing?
Changing variables.
Changing variables. Do you remember what you're changing them to?
I specifically remember doing the reciprocal. I want to say reciprocal equation is the terminology for it, but you turn it into lambdas.
Oh yeah, so we were eventually getting lambdas. So we were saying like u equals y and v equals y prime. And then what that means is that u prime equals y prime. But what is y prime? Perfect. And then, sorry, I wrote this wrong. I should have said v equals y prime. I flipped my primes. Let me fix that. So v was y prime, which means that v prime is y double prime. But from our equation, what do we know y double prime equals?
Negative ay.
Mm-hmm. Yep, negative ay prime minus by, which we can change into negative av minus bu. All right, so we did this whole change of variables, but what was the purpose of that change of variables? Matrix form, exactly. So putting it in matrix form, we had u prime, v prime equals, and then we are going to put our coefficient matrix and then a u and a v. So u prime was just v prime, u prime was just v. So we have 0, 1, and then v prime is negative av and negative bu, but putting those in the right place, we've got negative b and negative a. Is that okay? So if you multiply this out, doing matrix multiplication, we just get back to the same equations we had above. And then you took the eigenvalues of this coefficient matrix, right? So we had the eigenvalues of our coefficient matrix A. We kind of had two cases. We could have had two real eigenvalues. Let's call them alpha and beta. Or what's the other case you guys talked about? Yeah, two complex. So I'll call the complex ones alpha plus or minus I beta, because what makes it complex is we have the real piece and the imaginary piece. With the two reals, anybody remember what the form that had? For our solution, sorry. Yeah.
C1 times e to the first eigenvalue. T plus C2 e to the second eigenvalue too.
Perfect. And then what about with our complex case? Yeah, there were some cosines and sines in there. So it was y equals e to the alpha t, and then C1 cosine of beta t plus C2 sine of beta t. Yeah, so since I put the parentheses, you don't have to distribute the e to the alpha t, or you can write it out without parentheses distribute. Okay. What eigenvalue case did you not cover last week?
Real repeated.
Real repeated, yep. So our new case is we get one real, so it's a repeated eigenvalue. Let's go ahead and call that eigenvalue alpha. And then this one's going to have kind of an interesting form. We're going to talk about why in just a second. But the form is going to be y equals C1 e to the alpha t plus C2 x e to the alpha t. So both of our exponents in the e are going to be alpha, but in our second term, we're adding that x in there. So I think a really natural question is like, how did I decide that we needed an x? Like, where did this come from? It seems kind of out of nowhere. So why is this the case? Instead of doing a full-blown proof, we're going to do kind of like an example where we derive this second portion of it, but not a full proof of it. So I 100% lied to you. Well, yeah, I'm going to claim something without fully stating why it's true. So we're going to look at the case y double prime plus 2a plus a squared plus 2ay prime. I am just forgetting symbols all over the place today. 2ay prime plus a squared y equals 0. So I guess my claim to you is we will always get the repeated root when we have this case of an a squared and a 2a. That's the part I'm going to claim without proving to you, but it is true. And then we're going to use this to derive our equation, our second equation. So if we were to put this in our matrix vector form with our u's and our v's, our coefficient matrix would be 0, 1, negative a squared, negative 2a. And then if you ask like Mathematica or whoever to solve this for you and give you the eigenvalues, you would get exactly one eigenvalue, lambda equal to negative a. So we have one known solution, y1 equal to c1 e to the negative a t. But we want to get that second solution that we can add to it. Everybody with me so far? Kind of? Okay. So how can we get the second solution that we can add to it to get our overall solution? Last week, I know you guys talked a little bit about Abel's theorem. Ringing a bell? We are going to use Abel's theorem. So Abel's theorem told us that the Wronskian determinant of y1 comma y2 equaled C2 times the e to the integral, or e to the negative integral of e to the 2a dt. So Abel's theorem was a little bit more general. It just said that term in front of the y prime, but we know what's in front of the y prime, so I went ahead and threw that in there. And then if you integrate this, you get c2 e to the negative 2at. But we also know that the Wronskian determinant of y1, y2 equaled y1, y2 prime minus y2, y1 prime. So if we put in our y1s and our y2s and took a determinant, this was what we got. So I'm just going to set these two things equal to each other and solve. I know y1, that was c1e to the negative at. So plugging and chugging a little bit, I've got c1e to the negative at, because that's my y1, y2 prime minus, and then y1 prime is going to be a negative c1, so plus c1 ae to the negative at y2. That's going to equal c2 e to the negative 2at. What do you want me to do here? I think if I can get these e's to the other side, I will get something, and maybe even the c1s, I'll get something that's just like a y prime and a y, right? So it'll look like kind of a nice differential equation. So how can I accomplish that? Yeah, so I'm going to divide everything by c1 e to the negative at. So I've got y2 prime plus y2 equals, and then c2 divided by c1 is just another constant, right? I'm going to call that constant c. And then e to the negative 2a divided by e to the negative at gives me e to the negative at. Did I drop an a right here? Yeah, let me throw that in here. I dropped an a right there before my y2. Okay. Now how can I solve this? What was one of our first differential equation techniques? Yeah?
It's separation of variables.
This one you cannot do by separation of variables, but that's a good thought. What was our other technique? Integrating factor. What's my integrating factor going to be here? Perfect. E to the at. So if I multiply everything through by e to the at, I know I just got rid of a negative e, or e to the negative at, so it seems a little counterintuitive, but we need like the right signs working for us, right? So I've got e to the at y2 prime plus ae to the at y2 equals just c, because e to the negative at times e to the positive at, those are just going to give me 1. Then if I undo the product rule, I've got e to the at y2 prime equals c. And then if I integrate both sides, I've got e to the at y2 equals c t. I'm running out of variables. Let's go with k. because the integral of c is t, and then you always have that constant, that plus a k when you integrate, right? And then if we divide everything by y or e to the at, we get y2 equals c e to the negative at plus, dropped a t, I'm doing it again. Is anybody else having a hard time like keeping track of stuff when you're doing these problems? Yeah. So ct e to the negative at plus k e to the negative at. But this all the way from my beginning, this was my y1, right? I now have a new constant, but that's okay. And so overall, we've just shown that our general solution is y equals c1 e to the negative at plus c2x e to the negative at. Go ahead and end that proof. Yes, Evan.
Why do we use x?
Because I shouldn't be. The last time I taught any type of differential equations, we were using x's. So when I compiled these partially from those notes, and I forgot to just change the letter. Thanks for the catch. No, which is a fair point because I've thrown a lot of constants around today. Yeah. Any other questions? Sarah? Yeah. Yeah. So, right, I uploaded the good piece, and then the question was why, and the why is because of Abel's theorem. So we were able to pretty easily with our eigenvalue of negative a get one solution, but how do we get the other? You use Abel's theorem, but at the same time, you don't really want to have to repeat this, so you're allowed to jump straight to this is what I know the solution is going to be.
Also, when we're using y1 and y2, how do we decide which one to switch? Like, does it matter?
It actually doesn't matter. Y1 and y2 just means like what are two solutions.
Okay.
Because if you have two solutions to a differential equation, their sum is also a solution. Yeah. Other questions? All right. Then let's go to the board and do number 1 on your in-class assignment. Mm-hmm.